All right, here we go. Want to talk about the double slit interference pattern. And for reference, this is on page 40 of volume 5. All right, let's get this done. Oops. So, Young's double slit, famous experiment. You'll hear about it a lot in modern physics. So if you try to, it's all over the place. So let's learn this pretty well. We've actually seen it before when we talked about two source interference with sound waves. You could think about light coming towards these slits, and then you could view each slit as being like one of the speakers or one of the sources. Now, in this case, some parameters that we use are, in order to see this well, number one, we want to use coherent light, which means all the waves are in phase, they're cresting at the same time, and we want monochromatic light, one color. Back in the day, this was a challenge. You can read about it historically. Modern experiments, we typically use a laser, which is monochromatic, coherent light, very narrow wavelength band. D, this symbol, this parameter right here, is the slit separation. It's not the width of the slit. We'll discuss that more later on when we talk about single slits. But for right now, the only parameter we're going to care about is the slit separation, the distance between the centers of the slits. All right. L is called the distance to the screen. And when we shine light on the screen, we're going to get a pattern here where we see some bright spots and some dark spots. So why do we get these bright and dark spots? Well, light from one slit is traveling a different distance than light from the other slit. And so I don't want to cloud up this diagram too much, but maybe I'll give it a shot. So these two light rays, ray 1 and ray 2, do not travel exactly the same distance. Okay, so we're going to make an approximation here. The change in distance is approximately d sine theta. If I could take this piece right here and blow it up, we see that this little chunk is how much extra distance this ray travels. So if I draw that a little bit better, we get a right triangle. This side is D. And then if we do a little bit of geometry here, we can see that this angle here, you can say, oh, well, let's see, this angle here, this is 90 minus, that makes this theta. This top angle right up in here is also theta. All right, and I've got a good blow up in the handout to help you see that a little bit better. All right, and so this distance right here, it's opposite. All right, so I'll call this, well, if you do trigonometry, you will find this is d sine theta. Notice d is the hypotenuse, and this is opposite. So the path length difference is d sine theta, this little distance here. So delta r being the path length difference, that's not showing up. Whoops. Is that showing up? I can't see right now. Ah, there. Sheesh. This demo is, this was a tough one to film, everybody. So apologies if it's going to be a little long. All right. So there's the path length difference right there. And so that's what I was trying to say. D sine theta is the difference between ray 1 path and ray 2 path. Now, by the way, this is an approximation that's often but not always valid, especially for these optic ones. In sound, this is often not true, but in optics, usually the distance to the screen is much, much greater than the pattern. I'll show you a visual in just a minute. Okay, and so typically, I don't know if you can see this, but Sine theta is approximately tan theta is y over L. So, right, sine theta should be y over this, but think, if this angle is really small, the distance to the screen is almost the same as that length right up there, and that's pretty much true. All right, notice the angle is referenced to what I'm going to call the midline. The midline is the perpendicular bisector to the plane of the slits centered between the slits. I think it's a lot faster to say midline, and I think you'll probably end up saying it too, even though I don't know if anybody else says that, so that's just what I call it. Y is called the position on the screen, all right? So relative to the midline, all right? The screen, that's usually just a piece of white paper. Now notice this pattern is, I'm trying to show, obviously the light doesn't like make piles of crap building up on the screen, but what I'm trying to show here with the size of this is the middle of the spots are very bright and the edges of the spots are very dark, and then it goes completely dark in between the spots. So these dark spots are called dark fringes. This middle bright spot is sometimes called the central max. Okay, it's the central bright spot. All right, and this is called the, this is a dark fringe. So the dark spots are called dark fringes, and then notice you get a bright spot. This is called a bright fringe. The weird thing about it is the central max is not called a fringe. So the fringe is anything outside the central max. So you're going to have fringes, and the fringes can either be bright or dark, and then you've also got the central max. Now, the equations that govern this, if the path length difference is an integer number of wavelengths, right, the two waves will be cresting at the same time. Ray 1 and ray 2 will both be hitting a crest or a trough at the same time, and you'll get bright spots, bright fringes. That's constructive interference. So we say this equation, R plus or minus m lambda for m equals 0, 1, 2. All right, notice m equals 0 is the central max. 1 would be the bright fringe right here. 2 would be these two bright fringes, etc. Now, what if you have an odd number of lambda over 2s? Whoops, this thing, let me get this down a little bit. Put that back up in a sec. So if you have an odd number of half wavelengths, like 3 lambda over 2, 5 lambda over 2, that gives you destructive interference, right? One's hitting a crest while the other's hitting a trough. And so you'll get the dark fringes. And so we say that this way. I don't know if that's legible. I'm going to rewrite it just in case. You can see that. So in order to get the odd number of half wavelengths, we just do m plus a half, and then we can use the same integers for both of these. So that's kind of convenient. If you care, the brightness or the intensity of this pattern is governed by this function right here. It's 4 I naught cosine squared of phi, but phi has a sine in it, so it's cosine squared of something with a sine in it. Usually, this becomes y over L if y is much, much less than L, but strictly speaking, let's leave it correct as sine theta, and I'll just say often y is much, much less than L, sine theta is equal to y over L, approximately. Small angle approximation. So it ends up being not so ugly. It's basically, if you look at this, it's a cosine squared function of y. So as you go up or down, it's a cosine squared. Well, cosine squared is really bright at 0, then dark, then really bright, then dark, really bright, then dark. So this makes sense. Now, what does this look like physically? Let me go over here to 8, and we'll probably have to do a little bit of zooming around here. All right, so here is, let me move these so they're not distracting us. All right, here is a laser, here are the slits, and here's the screen, and you're just not gonna see that right now. So what I'm gonna do is try and make this look a little bit better. I'm gonna, just give me a second here, trust me. let's go 3. And then let's go over to here. Oops. And then let me go over to here. So right here, I have another one of these slits right here, and I'm just going to zoom in on it so you can see what it looks like up close. So let's go over there. Let's zoom in. Go up a little bit. Close enough. All right, and so what you can see here, there's actually two, it's basically a sheet of black plastic, and then they took a razor blade and cut these 2 slits out of it, or those 2 slits out of it. And what do these numbers mean? I have it written on the board here. Let me do this and go like this. The smaller number, A, is the width of the slit themselves. It's just how wide the slit is, and that's going to matter when we get to single slits. The bigger number here, that is the slit separation in millimeters. So these 2 slits are 1/4 of a millimeter apart. That's why you're never going to see this unless I zoom in crazy big. And now, so here's another thing. Let's go to the demo. And what I want to do is walk over this way. Give me a second. Whoops. And let me zoom out just a little bit. All right, there we go. So in order to make the pattern show up, let me move this table out of the way. I forgot to move that. All right. Make sure we're seeing everything okay. So what I can do is I can actually remove this screen and let the laser go all the way over to here, almost 5 meters away. This is 4.75 meters away. And then what I'm going to do is I'm going to turn out the lights to see if you can see this pattern right here. And then I will zoom in on that pattern in just a second. Give me a second. So again, just to be clear, the distance between the laser, or actually not the laser, but the slits right here, and this screen is 4.75 meters. I've got this all written down. And let's zoom in on this all the way we can. And I'll go up a little bit. And just barely, you can see the green pattern there. All right? So you can see, notice, the dark fringes are approximately equally spaced here. And then just for reference, I can tell that this one, it doesn't really matter, but I'm going to say this one is the central bright. Can't tell which one it is, but I don't really care. But I just want to point out the distance between adjacent dark fringes is almost exactly 1 centimeter with this color of light. So the distance from this dark fringe to that dark fringe is 1 centimeter, all right? Now, if we had more time, we'd do lots of careful measurements, but what I want to do now is come up here to this board. Let me get this screen out of the way. Just a sec. I suppose I should turn the lights on so you can read the board. Let me get this light on and turn that blue off. Just a second. Thanks for your patience. All right. So, I thought you would find this slightly interesting. Okay, what did we find here? We said that the dark to dark distance was 1.0 centimeters. It was 1 centimeter between adjacent dark fringes. So if I have my markers, here they are. We saw there was the central max, and then there was a bunch of fringes, and the dark to dark distance we found was 1.0 centimeters. So what I want to do is I want to make the following assumption. Y is much, much less than L. That allows me to take sine theta and turn it into y over L. And then I'm going to assume we were looking at the fringes on opposite sides of the central maximum. And this would have been true if we had looked at these two fringes or these two fringes. So that's not a bad assumption. Right? That's not a big deal. So look, there's going to be dy over L is equal to lambda over 2 for this fringe. So going from here to the first dark fringe, that's distance y. But notice if I cross multiply by 2, I'll get a 2y here, but 2y is the dark to dark distance. The distance between adjacent dark fringes. So now we can punch in these numbers. What was it? The diameter, the slit separation was, what did we say? 0.25 millimeters. 2y, the adjacent dark to dark, was, what was that? That was 1 centimeter. Here's my purple. Notice I basically got 2 sig figs here. And so out of all that, I found lambda, let me see if that shows up. It doesn't show up at all. I think it was 526 nanometers. Let me check my rounding. Where's my calculator? Come on. I had this somewhere. Yeah, 526.3 or something like that, which at first glance looks like it's quite off. This is the manufacturer's spec. So according to the manufacturer, that laser is putting out 515 nanometers, which, okay, we're off by 10 nanometers out of 500. That's only a 2% error, and because you can't read the screen, I might as well erase it. That's a 2% difference from manufacturer's spec. Whatever, from spec, all right? And that's one way of calculating, or that's one use of these double slits, is you could calculate the wavelength of light. So that's kind of handy. I guess another thing that you can do in practice, and maybe I'll mention this, we get this pattern of alternating bright and dark spots. You can actually, in a thing called photolithography, where you're putting some chemical on a semiconductor, you could shine this pattern on there and get alternating bright and dark spots and use that to make alternating spots of wire and insulator. So there's, more on this some other time. Let's call that video good.